Okay, so U-substitution. This video is going to be on U-substitution, and this is a Calculus 2 problem, and it says to evaluate the integral by using the U-substitution method, and it's the integral from 0 to pi over 3 for sine of t times 1 minus cosine of t raised to the third power. Okay, so when you're doing the U-substitution method, it's always good to look at what's in the integrand and try to see if any term is a derivative of a term that's inside of it or a constant multiple of the derivative of a term that's inside of it. So for U-substitution, I'm going to set U equal to cosine of t. And then we have to find what's du. So du is just the derivative of u. And if you have like an integral chart, which is always a good thing to keep on hand, you can use it on like calculus 1 and 2 tests. You can have like a note card with whatever handwritten notes you want on it, and it's always good to have like a derivative chart that you can refer to. And so I have a section that's called trigonometric derivatives, and I have the derivative of cosine of x, which in this case is cosine of t. So all this says is that the derivative of cosine of x equals negative sine of x. Translation, we're going to say that the derivative of u is going to be, which is the derivative of cosine of t, is going to be negative sine of t, and then at the end there we have times dt. Okay, so we've set u equal to cosine of t, and then we use this derivative, this trigonometric derivative rule, to find that the derivative of cosine of x is equal to negative sine of x. So we use this rule to solve for du. So we know that the derivative of u, or du, is equal to negative sine of t, and this is with respect to t. So we know that du is equal to negative sine of t. Look at the integrand above. We have sine of t, but we don't have negative sine of t. And this is the derivative that we get from what we set u to, namely cosine of t. So in a situation like this, we have to solve for sine of t. So we have du equals negative sine of t, right? And so now what we're going to do is we're going to divide both sides by -1. The result is going to equal negative du equals sine of t. So what we just did is we algebraically manipulated this. So now we have negative du equals sine of t. And this is good because we have a regular sine of t, a positive sine of t up here, if you will. So cool. But now we're going to just reiterate quickly that we have u equals cosine of t, and we have negative du equals sine of t. Before we plug in our substitutions, we have to evaluate the new bounds. And this is going to be our new limits of integration with respect to what we have just set u to, cosine of t. We have u equals cosine of t. Now we want to find the new lower bound. So we can do that by saying that u equals cosine of, and then what we have for our current lower bound in this problem, which is 0, cosine of 0 is going to equal 1. So now we have to find our new upper bound. So same sort of thing here, u equals cosine of, and then what our upper bound is, which is going to be pi over 3. And this is going to equal 1/2. We can plug in our u and du, or negative du, and our new bounds of integration. And just for specificity, we'll put this here. Negative du equals sine of t. We're actually going to find that the integral from 0 to pi over 3 of sine of t times 1 minus cosine of t raised to the third power is going to become something totally different. And we can plug in what we have done, right? So our new limits of integration or bounds of integration, you can use that term, you can use those two terms synonymously, um, is going to be, so down for the lower bound, we're going to have 1, right? Because that's what we said that was going to be over here. And then over here, the upper limit of integration, the upper bound of integration, is going to be 1/2. So 1/2. Now we're going to plug in our, our, uh, our u and our du, right? So, and I'm going to just use parentheses here. So this is going to become the integral from 1 to 1/2 of 1 minus u raised to the third power minus du, right? So now what I'm going to do is I'm going to factor out this minus sign. I'm going to factor that out. All right, so now what you can see that I did is I factored out the negative sign. And honestly, you can just imagine that this is a -1 in the front, right? So there's a -1 in the front because we factored out that negative sign. And we have the integral from 1 to 1/2 of 1 minus u raised to the third power times du. All right. So what we want to do is we want to flip the bounds of integration. And we want to flip the bounds of integration because we want the upper bound of integration or the upper limit of integration. Again, you can use these terms synonymously to be greater than the lower bound of integration. In other words, we want the lower bound of integration to be less than the upper bound of integration. And currently that's not the case. So we're going to flip this. But to flip the bounds of integration, there's a certain rule that you have to follow. And you have to multiply the entire integral, including what you factored out, and you have to multiply everything by -1, and then and only then can you flip the bounds of integration. And let me go ahead and just show y'all what I mean. So there's a standard property. Okay, so this is the standard property, and I just want to point out that this is the same thing as what we have right here. Okay, and then this is essentially the same thing as what we have here. And this, right? This is how you flip it, and what we did was we just multiplied this by -1, and it became this. So let me show you guys what I'm talking about here. So we're going to multiply these together. So we're going to multiply these together, and what that's going to do is allow us to flip these bounds of integration right here. These negatives right here, these negatives, they cancel. Okay, so this is what we get, right? And I'm looking at this and I can tell that I need to do a second round of U-substitution because this isn't explicitly U and du. There's a one right there. So let me show you guys what I'm gonna do, and we're gonna clean this up. So for the substitution here, I'm gonna use the term s. I'm gonna use the variable s. I'm gonna say let s equal 1 minus u. Okay, and then now I have to find the derivative of that. So find ds. Before we find the derivative, I just want to show you guys something really quickly. So we have s equals 1 minus u, and you can think of s as a function of u, meaning use the input and then s is the output that we get from u using the rule s equals 1 minus u. We are looking for ds over du. So du just means how fast does the output s change when I tweak the input u. And that's the concept of a derivative, right? So our function s equals 1 minus u is it's going to be linear, right? Because it's similar to y equals mx plus b. The slope m is the number that's going to be in front of u. But if we look at our equation, s equals 1 minus u, s equals 1 minus u can be rearranged to make the slope more obvious. So now we have s equals -u plus 1, which is equivalent to this equation here, s equals -1 times u plus 1. So now it's in standard form, y equals mx plus b, and we can see that m equals -1 because it's the coefficient in front of u. And then Likewise, the y-intercept b is going to be just 1. Therefore, ds over du is going to be -1. Okay, so this is one way to interpret it since it's linear, but I'm going to show you guys how to take the derivative directly from this function here. So the first thing that you want to do is apply the sum and difference rule for derivatives. Basically what it's saying is the derivative of a function plus or minus another function is equal to the derivative of the first function plus or minus the derivative of the second function. The first step to taking the derivative of this function here is to take the derivative term by term. So first we'll take the derivative of the constant 1. Now there's a rule to be applied to that. If you're going to take the derivative of a constant, any derivative of a constant equals 0. The derivative of 1 is going to be 0. So now let's find the derivative of negative u. Let's rewrite that. So negative u is the same thing as saying -1 times the variable u. And for a situation like this, we're going to apply the constant multiple rule for derivatives. So the constant multiple rule for derivatives is basically saying the derivative of a function times a constant is going to be that constant times the derivative of the function. So let's apply that here. The derivative of -1 times u is going to be -1 times the derivative of just u of prime. So the derivative of the derivative of -1 times u with respect to u is going to be equal to -1 times the derivative of u. But what's the derivative of u? So now we're going to apply the identity rule for derivatives. So this is the identity rule for derivatives. It's just saying that the derivative of any variable that's just by itself is always going to be 1. Okay, so now we're going to refer back to the constant multiple rule for derivatives, and we found that it's going to be -1 times the derivative of u, and the derivative of u is 1. So this is going to turn into -1 times 1, which is going to be equal to -1, right? But then we have to apply the sum and difference rule up here. So this 0 that we found when we took the derivative of 1, it's going to be added to the derivative of -u, right? And then -u is equal to -1 times u. And then the derivative of -1 times u is just going to be -1 times the derivative of u, and we found that the derivative of u is going to be 1, and then we did -1 times 1, which is -1, and then to apply the sum and difference rule for the derivative, we're going to just add 0, and then we get -1. So to reiterate, the derivative of this function here, -u plus 1, the answer is going to be -1, but we're not done yet. Okay, so now I'm going to clean this up. We have s is set to -u plus 1, and then ds over du is equal to -1. But we are specifically interested in ds alone, and so since we set s equal to 1 minus u initially, we can algebraically manipulate ds over du equaling -1 to get ds alone. All we have to do is multiply both sides by du. Okay, so we'll find that these du's cancel, and then we're left with ds equals -du. So I'm going to clean this up. Okay, so there's a problem here. So what's inside of these parentheses is the same thing as what we set s to, which we've shown algebraically. But there is no negative du, right? ds equals -du, and there's no negative du right here. It's not present. So ds is unable to replace this positive du here because ds is equal to negative du. So we need to replace du since that is what is in the integral. So we want an expression for du in terms of ds. So we can algebraically manipulate this again, set ds equal to negative du by multiplying both sides by -1. So let's do that. Okay, so we'll find that the negative term cancels out over here, and we're going to be left with negative ds equaling du. All right, so I just wanted to clean that up a bit. But now we're getting somewhere because we can replace the du within the integral. So we're good to go. But first, we have to evaluate our new limits of integration by plugging the upper and lower bounds into s equals 1 minus u as u. So after that, we can do substitution. All right, and now we're going to evaluate our new bounds. So we're going to evaluate the new lower bound via s equals negative u plus 1. What that means is we're going to do 1 minus 1 over 2, and that's going to equal 1/2. So that's going to be our new lower bound. And then we're going to do our new upper bound. So same thing, we're just going to plug it into our equation for s. S equals 1 minus 1, which is going to equal 0. So these are our new limits of integration. So let's plug them in. And so that's what this is going to look like. We plugged in our new limits of integration as well as our new s and our negative ds. So now I'm going to factor out that negative sign. So we're just going to flip the bounds of integration, but then to do that, we have to multiply the entire integral by -1. So let's do that. These -1s are going to cancel out, and we'll be left with the integral of 0 to 1/2 of s to the third power. So at this point, we're going to evaluate the integral. So I'm going to clean this up. So the first thing that we'll do is we're going to apply the power rule for integration. This is the power rule for integration, and we see that it can be applied because the n in this scenario, which is 3 here, is not equal to -1. So let's apply it. So this here is called the evaluation bar, and it's saying that we're evaluating it for 0 and 1/2, right? So to do this, we're going to apply the fundamental theorem of calculus. Okay, so the fundamental theorem of calculus shows that a and b are being plugged into the function, right? So this is what it's going to look like for us. So this is what it looks like for us, and we can see that this makes sense, right? So for b, we have 1/2, and then b gets applied to the function right here, okay? And then for a, we have 0, and a gets applied to the function right here. Great. So what does this equal? Well, we're going to work through the problem. 1/2 to the fourth power over 4 minus 0 to the fourth power over 4. I declared that it's the same thing as 1/2 raised to the fourth power times 1/4 minus 0 raised to the fourth over 4. Okay? And we can continue to work through this. Okay, so when you apply this exponent of 4 to 1/2, you apply it to the numerator, which is going to be 1, and then you apply it to the denominator, which is going to be 16, and then you still have to multiply it by 1/4. And then it turns out that this here, 0 raised to the fourth power over 4, is just going to go to 0. So now we're left with 1/16 times 1/4 minus 0. So we're going to multiply the denominators all the way through, and we're going to multiply the numerators all the way through, and that's going to give us 1 over 64. And that's going to be our answer.